Hi, I'm Wentao Huang from Stony Brook University. Today I will present our CVPR paper, Act Like a Pathologist, Tissue-Aware Whole Slice Image Reasoning, the work I did during my internship at the Mayo Clinic. Let me start with the task, Pathology Visual Question Answering, or Pathology VQA. Given a whole slice image, a model should answer natural language clinical questions about it, from diagnostic reasoning to report generation. If done well, this kind of model can scale pathologist expertise and deliver trustworthy answers. But the pathology VQA today has three different problems. First, a whole slide image contains far more information than necessary. And secondly, current whole slide image-based large language models treat every patch equally. And thirdly, predictions come out as black box without patch level attribution. Pathologists don't know which visual evidence support each answer. So our motivation here is simple and comes from the clinical itself. Pathologists scan broadly and then zoom in based on the clinical question. That's the human strategy we want our model to mimic. Before designing our framework, we ran a pre-analysis on a TCG breast cancer sample. Two findings here. The first is the patch question cosine similarity heat map closely overlaps with the tumor mask. And secondly, on the F1 curve for tumor patch retrieval, question-guided selection method is better than diversity-based and random sampling-based method across every token budget. Motivated by this, we propose HistoSelect framework. The framework has two stages. The first is tissue segmentation. It divides the whole slide image into M semantically coherent tissue groups, the segmentation map. And secondly, a hierarchical selector ranks each tissue group against the question, and then selects the most informative patches within each groups. For tissue segmentation, together with our pathologist collaborators, we design M tissue type prompts, including tumor, stromal, lymphocyte necrosis, and so on. And for every patch, we compute cosine similarity between conj visual embedding and each text prompt, and assign the patch to the most similar tissue group. This gives us a clip-style segmentation map of the slide, which we will use in the second stage. Stage 2 is the hierarchical selector. A group sampler predicts a sampling rate for each tissue group, and a patch selector then produces a selection probability, and we keep the top K patches for each group. Also, we use STE to make this selection differentiable, and the entire pipeline is trained with this final loss function. We evaluate our HistoSelect on three different datasets: Slide Bench VQA, WSI Bench, and our in-house ovarian dataset. Our HistoSelect achieve better performance in both closed-ended and open-ended tasks. For qualitative results, here is the before and after selection visualization. Before selection, patches are spread across the entire whole slide image, and after selection, non-tumor patches are filled out. Importantly, this removes about 70% of the visual tokens with no loss in performance. To conclude, HistoSelect brings a cross-defined question-guided selection mechanism into WSI VQA, and every prediction is now backed by a set of selected patches. Code and paper links are on the slide. Thank you for listening.